Hello everybody, I hope you are well today. We are going to talk about how to calculate the t-value while having two sets of data with a small amount of sample. Now this type of analysis was created to understand if two pieces of sample are significantly different from each other. Okay, and significantly different, considering that two things are, you're comparing two things and they're, quite similar. So you apply the null hypothesis, which means that if something, you're going to determine whether something is similar or significantly statistically different. Now, to do this, we're going to create normal distribution bell curve, and we're going to make certain calculations. But first, we're going to determine based on two data sets. So that's data 1 and data 2. And right here, we're going to put two random numbers. I'm going to generate a value applying rand between. Okay, and we're going to apply it between something, let's say between 10 and 25. Okay, so a base number is going to be 15. So I take 15 in both cases, and in one of them, I'm just going to add rand just for a random value, and in the second one I'm going to do the same. Okay, equals and then plus rand. Now this is something that I'm doing just to create two random values that I want to use. Okay, in the second case, what I'm going to do, just to make it just a little bit different and to see what I get, I'm going to add rand twice. Now remember that when you use the rand function, you're adding a number that is a fraction between 0 and 1. That's why you get all these decimal points. Okay, and now what I'm going to do is I'm going to do something with a relatively small sample, less than 50. So we're going to do something like around here, all the way up to this point. Okay, I have all these values. I'm going to copy and paste just simply the values so I don't have any more formulas. Okay, now the formula that we're going to be applying is the formula for the t-value, which is this formula that I'm going to show you here. This is what we're going to be applying. Now, as you can see here, we need the x value, which is the mean or the average of both samples, then the S1, which is the standard deviation, elevated to the square, which becomes the variance, and this is going to be divided by the count. Okay, now the first thing that we need to calculate is the mean. Okay, so we're going to calculate the mean from the first one, which is basically the average from all of the sample. Okay, that's mean 1 or x1. We're going to do the same thing for x2. Okay, we can see right there that the averages are a little bit different. The second one is a little bit higher, obviously, is what we were expecting. Then we're going to take the standard deviation. Okay, the stdev. We're going to take stdev. Okay, and stdev is going to select all of the sample as well. It's really quite a simple application of the formula. We're going to do the same with the second one. Then we're going to calculate the variance. The variance is the standard deviation elevated to the square. So we're going to take this one and we're going to elevate it to the square like this. Okay, we get these values. As you can see, it's elevated to the square right here. And then we're going to take the counts. Okay, so we take n1 and n2. So for this one, we're going to just apply the count like this, the count formula. Okay, there we go, 17 and 17, of course, in the second one. Now, for the next part of the calculation, we're going to calculate the following. First, we're going to calculate the top of the formula, which is the absolute value of the average for the first set of data minus the average for the second set of data. Now, I want you to observe the following. If we make a subtraction of the first value and the second value, of course, x1 minus x2, we're going to get a negative value in this case. But I want the absolute value. So I want the absolute value of the mean, which is exactly what the formula is indicating here. So I'm going to put, right before the subtraction, I'm going to put ABS, which is the absolute value of the two. So instead of being minus 0.334841, now it's 0.334841. It's a positive value. In the next case, we're going to do the variance, which is S1 in this case, S1 elevated to the square, which has already been elevated, right? S1 elevated to the square, and we're going to divide that by the count 1. Now, excuse me, the variance has already been elevated, so we don't need to elevate it anymore. So we're going to divide the variance by the count, like this. Now that's for the first one, and we're going to do the same thing for the second one. So that's S2 elevated to the square divided by N2, like this. Okay, so we're going to take the variance divided by the count, and we get this value. We get these two values. It's perfect. Then we're going to do the sum of the two fractions. We're going to do this fraction plus this fraction that we've already calculated them. Okay, we put the sum right here, so we're going to take this value, of course, plus this value, which right here we are emulating the sum of these two fractions. Okay, there we go. Then at the end, we're going to do the square root of all of the bottom of the division. Okay, we're going to do the square root of the sum, SQRT, of the sum. Okay, which means that we're going to do this one right here, and we're going to do the square root of that value, SQRT, okay, of the sum, of the result of the sum right there, and we get a 0.12. The last part that we're going to do is the division of the absolute value of the subtraction divided by the square root of the sum of the two fractions. Okay, so in this case, we're going to put the t-value, which is, of course, our objective. Okay, we're going to divide the value of the absolute of the subtraction by the square root of this, blah, 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 and we get a value of 2.77. Okay, now, the next part that we're going to do before we actually make the analysis about this, we're going to calculate the normal distribution for both of the data sets. Norm dist 1 and norm dist 2, like this. Okay, so we're going to do the formula norm dist just directly, like this. And the first thing that it asks us for is the x, which is the value that we are going to be using as our base, divided by the mean, of course, of the first sample. Not divided by, excuse me, we also consider the mean, and we also consider the standard deviation. Then if it's cumulative, no it's not, so we're going to do a false, which is exactly what we're doing. Now, if I stretch this down, of course, we're going to see a bunch of mistakes because we didn't fix the value. So we need to fix the value, and we fix it right here. The values that need to be fixed are the mean and the standard deviation. So I'm going to fix that one, and I'm going to fix that one too. So now the mean and the standard deviation have been fixed. So now I am free to do it, and there we go. It's perfect. It's only affecting that. So now what we're going to do exactly the same thing. Norm dist, like this. We select our x, which is our value from the data, the mean, the standard deviation, and false. And of course, we're going to fix the mean and the standard deviation. Very good. There we go. Excellent. Now we can create a chart for the normal distribution bell curve. Now for this one, I recommend using the 2D bar chart, which is this one. Okay, so we select the first one, that's fine, and it creates this, this really nice chart, okay? And we're going to call it the normal distribution bell curve. Oh, I'm going to move this down here just as reference. Okay, we're going to call this the normal distribution bell curve. Normal distribution bell curve. Now it doesn't look like a bell, but we'll make it look like a bell in a moment. But first we're going to include the data set for the normal distribution for the second data set. Now we go here to chart design, and then we go to select data. We add another series like this, and then we select our values for y. And we select the second column of the normal distribution. And we hit OK, and we get both values, but they still don't look like a bell curve. So what we're going to do is we're going to put them in order from the smallest value to the largest value. We go here to data, we click from A to Z, or A to Z, and we're going to get this notification, this warning. We're going to just choose continue with the current selection, not expand. Continue with the current selection. We're going to sort, and the only column that's going to be affected, or the only numbers that will be affected, are the ones that are selected. We click sort, and as you can see, we can see that the blue bars look a little bit more like a bell curve. Okay, then we do the same thing for data 2, like this. Again, we repeat the process, continue with the current selection, we go sort, and now we see the two bell curves, that they look quite nice, and now it's very clear that they're, a little bit different. Okay, so we look at the t-value right here, okay, and we go to something called the t-table, which is a standard thing that you can find on the internet. Now, usually for this, we have several columns, and the standard that is used in science, as I've heard from different sources, is of 5%, which is the column that has been selected that has been highlighted by the color yellow. As you can see here, we're choosing something that's 2 tails, and we're choosing 5%, which is this 0.05 is the same thing as 5%. Now, in our case, we have a certain amount of the degrees of freedom. Now, the degrees of freedom is something that I'm not notifying here, but we're going to call it like this. The DF, the degrees of freedom, I'm going to put here a note that is going to indicate what this is. The degrees of freedom, okay, degrees of freedom, which is something that we need to use the t-table. The degrees of freedom is DF equals, okay, N1 plus N2, and all of it we subtract 2, like this. This is the formula for the degrees of freedom. N1 plus N2 minus 2. So we take, again, N1 plus N2, okay, and we take this, we separate it in parentheses, so it's isolated from the rest of the equation, and we subtract 2, like this, so our degrees of freedom are 32. We go to our t-table, and we select, right here it says degrees of freedom. We go down to the number that is below 32, because there's no 32 in the table right here. There's no 32, there's a 30, so we take a 30. We don't take the higher one, we take the lower one. Okay, and it says that it has to be at 2.042 or below to be significantly similar. Okay, in this case we get 2.77, which means that we are going to reject our null hypothesis, that both of them are significantly different. Now we're going to repeat this process. We're going to do it with numbers that are a little bit closer to each other, okay? But we're going to do it a little bit quicker. We're going to copy and paste a lot of things, just with the objective of you noticing how they can be significantly similar. So we're going to do it again. We're going to do it with 15. Okay, and we're going to do plus rand, like this. We're going to do plus rand here. We're going to do this for 17 values, just like the other one. Okay, we're going to take it, we're going to copy it, and paste it. And these should be very similar to each other. Okay, so what we're going to do is we're going to copy all this stuff, copy everything all the way down here, except for the reject part. I'm going to erase that in a moment. So there we go. Okay. Our t-value is of 1.08. Then we're going to take our normal distribution again, norm dist 1, and norm dist 2. Okay, so we're going to take the formula right here. Let me see if I can copy it and paste that. I don't know what's going to happen. Copy and paste it over here. Did I get it? Yeah, there we go. I got it. Okay, perfect. So now we're going to move this over here. And it's going to keep the same ones. I don't want that. We just change this one to C, and we change this one to C, and that's it. Okay, great. Now we select all of this. Excuse me for that. You select all of this. You pull it all the way down, and we get all of these values. Okay, we're going to insert the chart for the normal distribution bell curve. You know what? You know what's going to be easier? If we... No, it's fine. Let's keep it this way. So we're going to insert the 2D column. Let's expand this chart just to look at it and see if they are significantly similar, and if we can perceive how significantly similar they are. Excuse me. Normal distribution bell curve. Okay, there we go. And then we're going to select the data for the second value, just like I explained in the previous worksheet. Okay, there we go. And we have both of them. Now we're going to order the data so that we can appreciate how the bell curve looks. Continue with the current selection. Yeah. The same thing with this one. Continue with current selection. Yep. And there we go. Now let's look at the value, at the t-value. It says 1.08. Now if we go to the t-value and we go that our degrees of freedom are 32, okay, we go to here 30, and it has to be at 2.042 or less. In this case, we are at 1.08, which means that we will accept our null hypothesis, which means that these two sets of data are significantly similar to each other, which is really great. It means that they are both similar, and we could prove that they are not significantly different, but rather significantly similar. And that's how you calculate the t-value and create the normal distribution bell curve. If you have any comments or questions, please leave a message right here in the comments. Thank you.